In this video, I'm going to be talking about Euler's method, which is a method we are going to use to approximate solutions to a differential equation. Most often, this is going to be, here's a differential equation. This thing is not separable, but I know that there's a solution to it, and I want to find out what the value of the solution is at, say, some random x value. So the question is going to look something like, okay, here's a differential equation. The derivative, the slope is given by x minus y. That is certainly not separable. There's going to be an initial condition, and they're going to want you to approximate y of 1 using Euler's method and two steps of equal size. Okay? Now, most often in the AP course, it's going to be two steps of equal size. I have seen maybe 3 steps, but in general, it's probably going to be 2 steps. That's what we're mostly going to do. Okay? In the textbook, it's going to ask you to do like 10 and 20 steps using a calculator. And yes, Euler's method is certainly useful, if you've got a calculator. But these days, you could probably maybe, I don't know if this thing does have a closed form solution, but lots of calculators can actually solve differential equations, so at that point it's kind of, might as well get the exact value if you can. So the idea here is, suppose you've got a slope field, right? I'm going to come back to this example. Right. So this is a differential equation free response question that we did sometime much earlier in the year, where you had to, sketch in the slopes on the slope field. Okay. And so what we're doing here is, say we know that f of 0 is equal to 1, something like this. And we want to know what f of 2 is. Okay? Well, if we use the tangent line approximation, which is something we definitely did at the beginning of the year, okay, we would say, okay, well, the tangent line to this thing is horizontal. It's y equals 1. So that would mean that our approximation for f of 2 would be 1, because it's just going flat, so I just presume it's going to continue to go flat. But we know just from looking at the slope field that that's not going to be right. See what I'm saying? Like, if you check back in at 1, you see that the slope is positive. So you know that f of 2 is most likely going to be greater than 1. Because then we also did the thing where we sketched the solution curves, where we followed the lay of the land or whatever, and you could see that this thing is going to look like a really shallow parabola, something like that. And so what we might do instead is, go for a while, then check back in with the derivative and readjust our trajectory so that we could say that f of 2 was a little bigger than 1. This is Euler's method. It's repeated tangent line approximations. Okay? When we studied in the last year, we studied the Taylor polynomials. We basically did tangent line approximations, but tangent polynomials, if that's even possible. And it was possible, and it was great. Okay? But this is just repeated tangent lines. So what we're going to do, the main method I'm going to show you how to do is just writing down repeated tangent lines. I will also show you the table technique, but that's not what I'm going to be doing in general. Okay, so back to our example. What we're going to need to do is we're going to need to, if we want 2 steps, we're going to need 2 tangent lines. So I'm going to start with tangent line 1. And I'm going to say, well, I need a point and a slope. Well, I've got a point is x equals 0 and y equals 2 from this initial condition right here. And then the slope, I've got an equation for the slope right here. Y prime is equal to x minus y. 0 minus 2 is negative 2. Okay? That means I'm ready to write down the equation. And that'll be y minus 2 equals negative 2 times x minus 0. Now, okay, if I'm going from x equals 0, the point I know, to x equals 1 in 2 steps, you might even draw out a little diagram over here and say, okay, here's a little number line. Here's 0, here's 1. 2 steps would be going to 1/2 first and then going to 1. So the first thing I'm going to plug in is x equals 1/2. So let x equal 1/2. I'm going to say y, I'm going to add 2 to both sides. So it's 2 minus 2 times 1/2 minus 0. So 2 minus 1 is equal to 1. So now my new point is going to be x equals 1/2, y equals 1. And then I've still got the same equation for the slope because the differential equation is valid for all points on these solutions. So the slope is 1/2 minus 1 is negative 1/2. So now I've got a point and a slope. I'm ready to write down my equation. That's going to be y minus 1 equals negative 1/2 of x minus 1/2. Now I'm ready to plug in x equals 1 because this is my second step, so I'm approximating the value of y where x equals 1. And y is going to equal 1 minus 1/2 of 1 minus 1/2 is 1/2. Okay, so 1 minus 1/4 is 3/4. What I will point out is that if you're taking steps of equal size, this number should be the same as this number. This thing that you get when you plug in x, if you've done your tangent line in point slope form, that should be the same. So if you're not getting the same thing and you're hoping that you're using, steps of equal size, you've probably taken a wrong turn somewhere. Okay. Here's one that I'm going to let you try on your own. Okay. And now this is not how they would ask this, right? They would give you much more explicit information, but this is kind of a, conceptual use of Euler method. Log of 1.4. Who knows, right? I know it's bigger than 0 because the log of 1 is 0 and log increases. But log of 1.4, who knows? I don't know what exponent I put on e to get 1.4. What I could do is I could approximate it using Euler's method. But what we don't have is I guess we know the function is y equals log x. The derivative, y prime, is always equal to 1 over x. Okay. And then I've got an initial condition. The one point I really know or the one grid intersection point on y equals log x is y of 1 equals 0. So when we're going to say y of 1.4 is approximately equal to what? So why don't y'all do that? I'll kind of draw out the number line again. Okay, 2 steps of equal size. If I'm going from 1 to 1.4, well, that middle point would be 1.2. So y'all try this. Okay. If you're watching at home, you should definitely pause the video because the answer is just about to pop up here in a second. Okay, here you go. And so I started with the point and the slope, and then I had the equation, and I said y was approximately equal to 0.2. Now, if we just use the tangent line approximation, boy, we'd have gotten, y equals x minus 1, and we'd have said it was, about 0.4. But I know that the graph of log is concave down. So really, the graph sits below the tangent line, so 0.4 would be an overestimate. So 0.3667, well, let's see. I mean, is that a good estimate of the log of 1.4? I don't even know. Not bad. It's much closer than 0.4. It's 0.336. Okay, so not that far off, not terrible at all. It was close, and before I had no idea what log of 1.4 is, and this is a pretty good guess. Next, I'm going to show you a kind of a different technique for how to organize your Euler method work. This is going to be the tabular method. I'll just say right off the bat, the disadvantage to this one is that you have to, kind of like memorize a formula. Okay, and there's already so much stuff for us to remember. We got to remember the Lagrange error bound. We got to remember the derivative of cosecant. I don't know. There's other things we need to know. How to take an integral. That should be second nature by now, but yeah, it's something you need to remember for sure. And there's enough stuff to remember. But I will show you, and this is actually probably what you would be instructed to do, say in a college calculus course, if they were going to ask you to use Euler's method and say like 5 steps or 10 steps or something crazy like that. Okay, so what we're going to do is we've got f of 0.2, and we've got all this information about these derivatives, and we want to approximate f of negative 0.2. So this one's going to go backwards. Okay. And yeah, so what I'm going to do is I'm going to kind of make a table with 3 columns. And we're going to start with the initial condition. I'm just really not a huge fan of this, but it's okay. So that's what I would do is I would say, I'm going to put, each of the individual x's there. I'm going to put the next n is approximately equal to the previous n plus dy dx multiplied by delta x. And then this will be yn. So my first one is, so it's if I'm trying to approximate f of negative 0.2 using 2 steps of equal size, I'm here, positive 0.2. I want to go to negative 0.2, and the middle will be 0. Okay. So the first one is going to be x equals 0. Okay. The next y, the next y is approximately equal to the first y, which we said was 1, plus dy dx. Okay, where was dy dx? It's in the table. It's right here, 1.7. And then delta x, in this case, we went backwards by 2, negative 0.2. Okay, that's not looking good. Okay, so 1 minus 0.34 is going to be 0.66. I'm concerned for this next step. Okay, but we'll see. Okay, then the next x value is going to be negative 0.2. And then y2 will be approximately equal to y1 plus dy dx at x equals 0, so that's 1.2 times negative 0.2. All right, so that'll be, well, that actually won't be that bad because I've got 66, and I'm going to subtract 24, and that would leave me with 42. This is the table method. Not my absolute favorite, but definitely something I wanted to show you all, so if that really sits well with you, if you like this is something you can do. Okay. The most important thing I can say about Euler's method, though, is that you need to practice it a bunch of times. It was one of those things when I had calculus every day for 90 minutes, I hit this at like 3 different times throughout the year, just so they wouldn't forget. It's the type of thing I guarantee it's going to either show up on the multiple choice or the free response of your AP exam, probably just once, but it's easy enough that we really want to get it right. Okay. So I think, with the time I have left, I'm going to do 1 or 2 more examples, and, you can just do them however you feel. All right. The next one I've got for you is probably as complicated as the differential equation would look, but the thing is that this differential equation is separable. So I can find the particular solution just by, I guess, dividing both sides by y. Now, it would probably be a pretty unpleasant one. There'd be logs on both sides. Lots of opportunities for algebra errors. But we could find the particular solution. We could plug in 0, and we could get, we could get the exact value of f of 0. The thing is, well, we're doing Euler's method. Let's just do it. Okay. So y'all try this one. Okay. Oh, and you're going to need to use 3 steps of equal size. Let's kind of beef this one up. Use Euler's method in 3 steps.
Questions on the AP test be this direct?
Yes, it will call Euler's method by name every time, and it will tell you either. And maybe I should have, it'll either say and 3 steps of equal size or and 2 steps of equal size, or it will say and step size, in this case, step size 2, right? Because this is going to have to be step size 2 if I'm going from 6 to 0 in 3 steps. Okay, I'll even draw us a little diagram here. Going from 6 to 0 in 3 steps, well, that's 2 and that's 4. Okay. So we're going to need, either 3 tangent lines or 3 rows on the table, something like that. I'm going to use repeated tangent lines because I kind of like that. But you do it however you feel. If you're watching at home, again, you should pause the video because I'm just going to work it, and then you can check your answer against mine. All right, there you go. Okay, I ended up getting 0, which is what I got, on this problem. I'm looking over at this binder that I've got from, I don't know, like 4 years ago or something, and that's what I got then too, so I'm feeling pretty good about it. There's going to be a pretty beefy homework just on Euler's method, and, lots of practice opportunities. Okay, don't forget about your multiple choice free response. I'm going to kind of just link you the Unit 5 stuff, and oh yeah, the last thing I was going to point out is, remember, you should always be multiplying the slope by the same number if the step sizes are equal. Okay, so notice it was -2 each time. Okay, that's a good check along the way to make sure I'm doing it right. It's that you should see the same number appearing each step. And that's all I got for you today.